Hello, geometric again. Before I get started with part 2 of Laplace transforms, where I'm going to be using the Laplace transform to solve a third order differential equation, there's a number of preliminaries I'd first like to get out of the way so that particular video doesn't take so long. In this video, I'm going to be deriving some trigonometric identities using complex numbers, and we'll be using one of the forms in particular in the solution of a third order differential equation using Laplace transform. So rather than spending all the time in that particular video and lecture, we'll do it in this one and just use the results of what we derive here in the subsequent video. So now we'll get started, but before I get into the derivation of the trigonometric identities with the complex numbers, I'm briefly going to discuss the structure of the number system and to show why we're using complex numbers. We need complex variables in order to solve differential equations using the Laplace transform. If you remember from part 1 of the Laplace video, I discussed where the operations of integration and differentiation become division and multiplication by the Laplace variable s in the transform space. So what happens when you're transforming a differential equation into the Laplace space? You end up with a polynomial in S. And in order to put the transformed equation into a form where you can transform back to the original space that you started from, you have to find the roots of a general polynomial equation, which in general can have complex roots. Any polynomial equation with real coefficients has solutions both in the real numbers and also in the complex numbers. So we need to understand how to manipulate complex numbers in order to effectively solve differential equations in the Laplace space. So now I'll just briefly discuss the structure of the number system. We first start with what are called the counting numbers. These are the numbers, positive integers without zero, 1, 2, 3, 4, what we call the counting numbers. Now, the whole numbers we designate by capital W, and the whole numbers are the counting numbers plus 0. We add 0 to the counting numbers. So we have 0, 1, 2, 3, 4, 5, so on up into infinity. It's 0 plus the positive integers. We call these the whole numbers. Then there's the integers. The integers we designate by capital Z, and these are both positive and negative integers. The integers are what we call closed under addition, subtraction, and multiplication. What we mean by closed is if we take two elements in the set, in this case two integers, and we perform an operation, any one of these three operations, we will also get an integer back. So we have an element, we operate on it, and we get the result, which is also in the set that we started with. But the integers are not closed under division or taking a root. For example, if I divide 2 by 3, we don't get an integer. Or if I take the square root of 2, we do not get an integer. So division, multiplication do not result in an integer solution. So we say that the integers are not closed under division and taking a root. Now we take, and if we ratio two integers, p over q, where both p and q are elements of the integers, and we ratio two integers, we have what we call rational numbers. A rational number. The decimal representation of a rational number has a repeating digit, sequence of digits after a specific sequence. For example, 7 divided by 4 is 1.75000. So it repeats zeros after the third digit. 20 divided by 7 is 2.85714, 2.85714, 2.87154. So this sequence of digits, this six-digit sequence, gets repeated forever and ever. This is characteristic of rational numbers. You always have a sequence of repeating digits after the first sequence, and it just repeats itself forever. Now, if you ratio 20 by 4 and get 5, this is not an integer. An integer is not of the form p over q. Any form p over q using integers is called a rational number. Now, it just so happens that this particular rational number is equal in value to an integer, but it is not an integer. 20 divided by 4 is not an integer. It's a rational number because integers are not of this form, p over q. 5 is an integer. 5 over 1 is not. 5 over 1 is a rational number because it is a form p over q. Integers just have, you could say, a p form, just one. You don't have a numerator over a denominator type representation. Now your integers, or the rationals, are closed under addition, subtraction, multiplication, and division, but not in taking a root. If I divide two rational numbers, I get a rational number back. Or if I add, subtract, and multiply two rational numbers, I also get a rational number back. But if I take the root of a rational number, square root or a third root of a rational number, I will not necessarily get a rational number back. For example, the same thing as we had here is if I take the square root of 2, I get what's called an irrational number, not a rational number. The irrational numbers we designate by capital I, and these are numbers that have non-repeating decimal forms. Examples would be the square root of 2, pi, e, square root of 17, and the third 2 plus the square root of 3. These numbers and any irrationals have decimal representations that just go on and on forever, like a random sequence that never ever repeats. Now, any irrational number that is not a solution to a rational equation is called a transcendental number. Transcendentals are a subset of the irrational numbers. Pi is transcendental. There is no polynomial equation or rational equation for which pi is a solution, so we call it transcendental. These are the irrationals. Now the reals we designate with capital R. This is the union of the set of integers, rationals, and irrationals. All numbers on the real number line are represented by the real numbers, all points on a line. The reals are closed under addition, subtraction, multiplication, division, exponentiation, and taking the root of positive numbers, not the negative numbers. So the reals are not closed under taking the square root, for example, of a negative number. You could take the third root of a negative number and get a negative number back, but you cannot take the square root or even number roots of negative numbers. For example, if, say, y is the square root of minus 1. This implies then that y squared is equal to minus 1. There is no real number. No real number exists such that if we square it, we get a negative number, like minus 1. So no real number exists such that its square is negative. So that's why the reals are not closed under taking the square root of a negative number. Now, the last set of numbers in our number system are called the complex numbers. We designate it by capital C. We define the imaginary unit, I, as a square root of minus 1. Now, I may at times slip and call square root of minus 1j. Engineers, electrical engineers, call the imaginary unit j. Mathematicians call it I. I will try to use the mathematical designation I, but I may slip up from time to time and put j down on the board or call it j, so don't let that bother you. I and j both represent the square root of minus 1. Now z is called a complex number if z is written in this form. Z is x plus iy, where both x and y are elements of the real numbers. They belong to the real numbers. So we could write a complex number z, let's call z1 is 3 plus I 0.5. That is a complex number. Both 3 and 0.5 are elements or belong to the real numbers, and when we put it in this form where we have I times a real number, it now becomes a member of the complex numbers. The complex numbers are closed under all algebraic operations. We call the complex numbers complete, which means that if I operate on a complex number, some algebraic operation, then the result also belongs to the complex numbers. Unlike where we had an integer, if we take two integers and divide it, we might not get an integer back. We'll end up maybe with a rational or some other real number. But the complex numbers are complete. Any algebraic operation we perform on complex numbers, we get a complex number back. Now I'm going to get started discussing complex arithmetic. We define a complex number z as x plus I y, where both x and y are elements or belong to the real numbers. And I is defined as the imaginary unit square root of minus 1. Now, if z is equal to x plus iy, then we define what we call the conjugate of z. And we designate the conjugate by putting an asterisk above the number. So the conjugate is z of z is x minus iy. The conjugate has the imaginary portion negated, opposite of what z is. Now we call the x in the real portion of the complex number, we call this the real part of the complex number. This x is the real part of z. Y is called the imaginary part of z. Now the imaginary part is a real number, not iy. Iy is not the imaginary part, just y is the imaginary part. And we define the magnitude, or the modulus of z, as the square root of x squared plus y squared. And I often designate this with a capital letter R for the modulus. And that's what I'll be using in my discussion. And I don't like writing square roots, so I try to avoid it as much as possible. And I'll leave answers a lot of times in this form where the modulus is x squared plus y squared, the modulus squared. And I'll write it out that way so I don't take the square roots. To get R, we just take the square root of x squared plus y squared. But I prefer writing moduli in this form, or the magnitudes in this form, so I'm not writing the square roots all the time. Now, a property of the complex arithmetic is if I take a complex number z and add to it its conjugate, divide by 2, this is equal to x. We can see that. If I add these two, the i's cancel and I end up with 2x. Z plus z conjugate is 2x. So z plus z conjugate divided by 2 is just equal to x, which is the real part of z. And in a like manner, if I subtract the conjugate from the complex number, I get, and divide by 2i, I get y, or the imaginary part of z. Now, if we look at it, z minus z conjugate, the x's cancel, I get iy plus iy. So z minus z conjugate is 2iy. So if we divide by 2i, we get the real number y, which is the imaginary part of z. A complex number can be graphically represented using a set of Cartesian coordinates. If we establish a set of coordinates at right angles to one another, where the horizontal axis is the real axis, and the vertical axis we call the imaginary axis, the complex number z, which is equal to x plus iy, can be represented in the plane, which we call the complex plane. We can represent a point in the plane for z by going along the real axis from the origin, a distance x, and going up vertically along parallel to the imaginary axis, a distance y. This becomes x plus I y, this point in the complex plane. Now, the modulus, or the magnitude, is nothing more than the distance from the origin to the point in the plane. The modulus, or the magnitude r, is, by using Pythagoras' theorem here, we have r is equal to the square root of x squared plus y squared. And that's how we define the complex numbers. So we see that graphically it's very easy and handy to represent a complex number using a Cartesian set of coordinates in this fashion. Now let's look at the imaginary unit I. If we take I and raise it to various powers, let's see what happens here. If we take I to the first power, that is I. If we take I to the second power, that's I times I, but I is the square root of minus 1, so I times I is the square root of minus 1 times the square root of minus 1, which is just minus 1. I cubed is I squared times I, or minus 1 times I, or minus I. I to the 4th power is I to the 3rd power times I. So that becomes minus I times I. And again, we have I times I, which is minus 1. So this is minus 1 times minus 1, or a positive 1. Now, if we take I to the 5th power, it's I to the 4th power times I, or plus 1 times I, and we're back to I. I to the 6th power is I times I, or minus 1. I to the 7th power is minus 1 times I, which is minus I. I to the 8th power is minus I times I, which gives us the same thing as here, or plus 1. So we see that raising I to a power is cyclic. After I to the 4th, we end up repeating. Now let's see what happens when we represent powers of I graphically. If we take the complex plane, we have the real axis, the imaginary axis, and let's set off our points. This is plus 1, this is I, this is minus 1, this is minus I. Now, if we look at what happens, let's put I to the 0 power is just plus 1. Anything to the 0 power, even in complex arithmetic, is plus 1. So I to the 0 power is just plus 1. Now, I to the 1st power is this vector that goes from the origin to the point I. And then, if we take I squared is minus 1, so it's a vector that goes to the left. And if we take I cubed, that is minus I. And if we get I to the 4th, we're back to I to the 0. Now look what happens here is every time we multiply I by itself, the vector rotates by 90 degrees, or pi over 2. If we take I and multiply it by I to get I squared, this vector rotates counterclockwise. And the same thing here. If we start with I squared, we multiply by I, we rotate the vector counterclockwise. So multiplications by I in the complex plane, any complex number multiplied by I rotates that vector 90 degrees, or that the vector that represents the number z, or a complex number in the complex plane, it gets rotated by 90 degrees. And I'll show you that here shortly. We'll prove that. One of the most important relationships of all mathematics, or is arguably the most important relationship in all mathematics, is what's called Euler's identity. It's where we take the constant e and raise it to the power of I theta, where theta is an angle, and that is equal to the cosine of theta plus I sine of theta. E is the constant called Euler's number, which has the value 2.718281828, and then it goes on forever, but it doesn't repeat this sequence of digits. It just happens to at the beginning. This is an irrational number. It never repeats as we go on out as many digits as we want. It's just like pi. It never repeats. But it just so happens that we have the first set of sequence of pi being the same sequence of numbers, but that only holds for these 8 digits here. After that, it doesn't repeat. Now, this is a very, very important identity. It establishes the relationship between an exponential and trigonometric forms. Trigonometric functions like sine and cosine, I will show you in a little bit, can be written in terms of exponentials. So basically all elementary functions except for polynomials can be considered as exponentials or written in exponential form. Now look what happens when the angle theta becomes pi over 2. E to the I pi over 2 is equal to I, because the cosine of pi over 2 vanishes. It is 0. And the sine of pi over 2 is equal to 1. So we end up with just e to the I pi over 2 is equal to I. We can represent a complex number in the complex plane graphically, which I just showed you. The geometric interpretation is such that if we have a horizontal, real axis, vertical, imaginary axis, we pick a point in the plane for z, then the distance from the origin out horizontally is the real part, or x. The distance up off the real axis is the imaginary portion, or y. And now we add the interpretation of the angle theta. Theta is the angle measured counterclockwise from the real axis to the vector that represents the point in the plane, from the origin to the point in the plane. And again, the modulus, or the magnitude, is just that distance from the origin to the point. What we have here is a right triangle. So we can use trigonometric forms to represent our values for x and y. If z is x plus iy, then x is a projection of this vector down onto the real axis, which is the magnitude or the hypotenuse of this triangle times the cosine of theta. Y is the magnitude or the hypotenuse times the sine of theta. Now, we can rewrite this solving for cosine theta. We have the cosine of theta is equal to x over r, and the sine of theta is y over r. Now, if we put these into this equation, into Euler's identity, we end up with e to the I theta is equal to x over r plus I sine of theta, which is y over r. If we multiply through by r, we get r e to the I theta is equal to x plus iy, which is our complex number z. So in general, z then is r e to the I theta, where r, again, r squared is x squared plus y squared. You can see that from this right triangle. The magnitude squared is the horizontal component squared plus the vertical component squared. So here we have a representation for our complex number z. Now what we have, this form here, r e to the I theta, we call it a polar form. It is a way to represent a point in the plane by a radial distance out from the origin plus the angle that that vector sweeps through to get to that point, the angle theta. And then the other representation we call the rectangular form, x plus iy. And if we put in for x, r cosine theta and r sine theta for y, then we can write r equals z equals Here we have e re to the I theta, which is equal to our x, which is r cosine theta, plus I r sine of theta. This, again, we call the trigonometric form, and this is the polar form. And this is the trigonometric form. Or the rectangular form, where we have x plus iy. So this is the connection between the polar and the trigonometric form for a complex number, is we use Euler's identity to get this relationship. It's a very, very important relationship. Now let's look at the angular relationship between a complex number and its conjugate. Z, which is a complex number, we represent it again as r, the magnitude of e to the I theta, but in this case I'm going to call this theta z, so we can keep track of which angle belongs to the complex number and which one belongs to its conjugate. And this, using Euler's identity, is r times the cosine of theta z plus I times r times the sine of theta z. Now, the conjugate of z conjugate, is r e to the I theta z conjugate, to differentiate it from theta z. And this is equal to r times the cosine of theta z conjugate plus I r sine theta z conjugate. Now, let's form a ratio between the imaginary and real parts for both the complex number z and its conjugate. In the complex number z, the imaginary part of z over the real part of z is just r sine theta z over r cosine theta z. The r's cancel, and this sine divided by cosine is the tangent function. So this is the tangent of theta z. Now, the imaginary part of z conjugate to the real part of z conjugate is r times the sine of theta z conjugate over r cosine theta z conjugate. Again, the r's cancel, and sine over cosine is the tangent of the angle theta z conjugate. Now, z, remember, is x plus iy, written in rectangular form. And the conjugate is defined as the opposite of the imaginary portion. That is, we negate the imaginary portion. If z is x plus iy, its conjugate is x minus iy. Now, if we take, again, the imaginary part over the real part for z, the original complex number that we started with, the imaginary part is y, the real part is x. For the conjugate, the imaginary part is minus y, and the real part is x. So we see that the tangent of z and the tangent of tangent of theta z and the tangent of theta z star are opposite one another. So we get the tangent of theta z is equal to minus, or let's say the tangent of z conjugate is minus the tangent of theta z. So the angles are opposite. graphically, what we have is this. If this is z in the complex plane, we have y and x, then z conjugate is just reflected about the real axis. So this is z conjugate. If this is theta z, then z conjugate, the angle for z conjugate is just minus. If we take the inverse tangent on both sides here, we get theta z conjugate equals minus theta z. So the angles are opposite between a complex number and its conjugate. Now let's look at what happens when I divide a complex number by its magnitude or its modulus. If I take z and divide by its magnitude, then I have z divided by r. r is equal to the magnitude. And this comes out to e to the I theta. We can see that from here. If I divide z by r, z divided by r is rei theta divided by r, and the r's cancel, and we just end up with e to the I theta. Rather than designating conjugates angles as theta z star and the original complex number is theta z, we just use theta, and we know that through this exercise that for the conjugate, that the theta for the conjugate is opposite that of z. For example, if z equals r e to the I theta, then z conjugate is written as r e to the minus I theta. Now this, remember on Euler's identity, we can write this now as cosine theta plus I sine theta. Well, what is the magnitude of this? If we take the magnitude, this is our x, this is our y, and remember r squared is the real part squared, which is cosine theta squared, plus the imaginary part squared. And this is a trigonometric identity. Sine plus cosine, or sine squared plus cosine squared, is equal to 1, identically equal to 1. So this expression for z over its magnitude, z divided by the magnitude of z, has a magnitude of 1. And we can easily see that. The magnitude of z is 1. And we divide by its magnitude, so the resulting magnitude has to be 1. So all points of any complex number, if you normalize by dividing complex numbers by their magnitude, they all lie on the unit circle, where the circle has radius 1. So z divided by the magnitude of z all lie on a unit circle. Now remember when we had I and we raised it to an integral number of powers, that it had the effect to rotate the vector representing I counterclockwise by 90 degrees for every power that we raised I. Now we can easily see that using Euler's identity. Euler's identity tells us that e to the I theta is equal to cosine of theta plus I sine of theta. Well, when theta is pi over 2, we have e to the I pi over 2 cosine of pi over 2 plus I sine pi over 2. Well, the cosine of pi over 2 is 0. The sine of pi over 2 is 1. So we're left with I. Now, if we raise I to a power n, say I raised to the n power, we use the polar form. We have e to the I pi over 2 to the n. And using properties of exponents, remember, if we have a base e raised to a power a, and then we raise that to a power b, we just multiply the exponents. So what we end up with here, e to the I pi raised to the n power, is e to the I n pi over 2. So what happens every time we increase n, we see that the angle increases by pi over 2. Suppose we want to know what I to the 26th power is. Remember that the powers on I are cyclic. For every fourth time we raise the power, we're back to where we started, is with I in the complex plane. If this is I here, the vector representing it, now if we square I, we rotate the vector 90 degrees counterclockwise, and we get to minus 1. This is I squared. And then again, if we multiply I by itself, we rotate again another pi over 2, and we get to minus I. And that's what this equation is telling us. For every time we increase n by an integer, we're increasing the angle by pi over 2. So I to the 26th power would be e to the I pi over 2 raised to the 26th. Then this becomes e to the I multiplying pi over 2 by 26. We get 13 pi. Now remember, there are 2 pi radians. One complete revolution around a circle is 2 pi radians. So all we have to do here is find how many complete revolutions around we've made. So if we take 13 pi and divide by 2 pi per revolution, this tells us that we have 6 1/2 revolutions. So we've made 6 complete trips around. So we can subtract off from the 13 pi the number of complete trips around. So we have 13 pi here, and we subtract off 6 times 2 pi revolution, 2 pi radians per revolution. We've made 6 complete trips around. So we have 13 pi minus 12 pi, and we're left with just 1 pi left over, which tells us that we are now sitting at minus 1. So e raised, or I raised to the 26th power is equal to e, or I, sorry about that, I to the 26th power is e to the I 13 pi, which is the same as e to the I pi. Because we subtract off 12 pi from this, it gets us to the same spot. So e to the I pi is just minus 1. If you put in here, if theta is equal to pi, the cosine of pi is minus 1, the sine of pi is 0. So we're at minus 1. So, or this tells us we just rotate the vector from 1 pi radians, and that puts us over at -1. If we rotate our vector pi radians in a counterclockwise direction. So that's how you can easily find powers on I. What they're equal to is, again, another example here would be, suppose you want to know I to the 117th power. Well, it's very easy. Again, this is e to the I pi over 2 times 117. So all we have to do is write pi over 2 times 117, or write this as an even number plus 1, or 116 plus 1, and we divide through by 2. So this is pi times 2 goes into 11 5 times, and 2 goes into 16 8 times, and then we have plus 1/2 dividing through by 2. So we have 58 plus 1/2 pi, or 58 pi plus pi over 2. We find out how many revolutions are in 58 pi. So we take 58 pi, divide by 2 pi. So we find that there are exactly 29 complete revolutions. So this gets us back to where we were at the starting point. We can ignore that. So what we're left with, this is the same as e to the I pi over 2, which is just I. So I to the 117th power is equal to I. Now let's see what happens when we multiply a general complex number by I. Here we are in the complex plane. We have the real axis, the imaginary axis, and here's a point in the plane, our general complex number z. Z is equal to x plus iy. Again, the vertical distance parallel to the imaginary axis is the y, the imaginary portion. The x portion along the horizontal axis from the origin to the x component of the point is the real part. The angle theta is the angle that the vector representing the complex point z is, that angle with respect to the positive x-axis in a counterclockwise direction. Now, here we have z is equal to x plus iy. Now we multiply the complex number z by I. So we have iz, which is I times x plus I times I, or I squared y. Multiplying through, we have ix, I squared is minus 1, so minus y, and I just rewrote it here. Our real part is minus y. The imaginary part is x. So that's what I have represented here. Iz is this point, which now the real part for Iz is minus y, and x for the imaginary part. Now what is this? What are the angles here? So let's put it in polar form. Z is equal to r e to the I theta. So Iz is Iz times I r e to the I theta. But in polar form, we can represent I as e to the I pi over 2. I just swapped I and r here. So I have r times I times e to the I theta. I is this portion, e to the I pi over 2. And using the rules of exponents, if we have e to the a times e to the b, then this is e to the a plus b. When we have the same bases multiplied by different exponents, we just take the base to the sum of the exponents. So we end up now with r e to the I theta plus pi over 2. So we see what happens when we multiply a complex number by I. We rotate the vector representing the complex number z by pi over 2. We're just adding pi over 2 to theta, or 90 degrees. So if this is z, then we've rotated by pi over 2 when we multiply the complex number by I. So every time you multiply any complex numbers by I, it has the effect geometrically to rotate the vector that represents that point counterclockwise by 90 degrees, or pi over 2. Now, in electrical engineering, in circuit analysis, and in traveling wave problems, in electromagnetic theory, rather than theta, a lot of time what we do is we represent theta by omega t, where omega is a angular velocity. Omega is equal to 2 pi f, where f is a frequency of an AC signal. We can represent omega as the time derivative of the angular position with time. This is what's known as angular velocity, or radian frequency, angular velocity in radians per second, and theta is angular position in radians. And that's in radians. Now, so what we can do graphically in electrical engineering in representing AC signals is that we have a vector going to a position in the complex plane, and again angle theta is measured with respect to the positive horizontal axis, and the angular frequency omega is the rate at which this vector rotates around. And this is a spinning vector, and a lot of times this drops out of equations, but this represents a spinning vector where omega is angular velocity, and as we multiply velocity by time, we have position at a new time. So this vector is spinning around at the rate of omega, and we call this a phasor. This was originated in General Electric by Steinmetz. He coined this term phasor for representing a spinning or a rotating vector. And I'll get more into this much later. Now, before I get into the derivations, I just have one last topic to consider here. Let's look at graphically what happens when we add and subtract a complex number and its conjugate. Now remember, the complex number z equals x plus iy, which is r e to the I theta, and its conjugate is x minus iy, which is r e to the minus I theta. Keep wanting to write j. All right, now if we add the complex conjugate to the complex number, what happens? The imaginary parts drop out, and we end up with 2x, which is twice the real part of the complex number. This is a pure real number. All the imaginary components drop out. So what this looks like, if we put it in our complex plane, if this is point Z, and here's our angle theta, remember now for the complex conjugate, it's reflected about the real axis at the same angle theta. This is Z conjugate. Now if we add these two vectors that represent this complex number, we have, this is Z, so we add this vector, complex conjugate, to Z. We have Z plus Z conjugate. So Z conjugate is this vector here. I'm just representing it parallel to this vector. I'm adding tail to head, tail to head. So our result is here. We take Z, we add Z conjugate, and we end up on the real axis at twice the real part. Here's the real part, and here's another real part. So we have twice the real part of Z here. Just as the mathematics shows us, it's pure real. We end up back onto the real axis. Likewise, this is what happens, similar thing happens when we subtract the conjugate from the complex number. So if we look at here, if we take Z and we subtract off Z conjugate, we have x minus x, which is 0, and then iy minus a minus iy, or we add 2iy. And this is twice the imaginary part of Z. And this is pure imaginary. So graphically, what we have is if we, here's our Z, vector representing the complex number, theta, and here's our complex conjugate, again, angle theta, but this time we're subtracting. So to Z, we're adding a negative conjugate. The negative conjugate is a vector pointing this way from Z towards the origin. If this is Z, this is, or if this is Z conjugate, this is minus Z conjugate. So we add it to Z. So we take this vector and add it. Here, get this off. And we add, we just move this vector over parallel, and we end up on the imaginary axis. And again, if this is one imaginary component, imaginary part of Z, then this is a second one. So this distance is twice the imaginary part of Z, just as this shows. Now what's happening here, as you can see, is that in the case where we're adding a complex conjugate to Z, the vertical components cancel. For Z, this is the vertical component, or the imaginary part, and for Z conjugate, that's the imaginary part. These two vectors cancel, and we just add the horizontal components. So we get twice the real part. Likewise, when we're subtracting the complex conjugate from the complex number, the horizontal components cancel, because here is the horizontal component of vector Z, or of the vector that represents a complex number, z, and the horizontal component representing the complex conjugate, or minus the complex conjugate, is this vector. So these two vectors are equal in opposite direction, and they cancel, and we just end up adding the vertical components. So that's the graphical interpretation using vectors. So you can see that the complex numbers and vectors are closely related, and we can do a lot of vector representations and operations in the complex plane using complex number. It's very powerful. Complex numbers are very powerful. Now I'm going to cover one last subject in the arithmetic of complex numbers, and that's having to do with conjugates. Suppose we have two complex numbers, z1 and z2, and we add them together, and then we take the complex conjugate. Well, the complex conjugate distributes through the addition, and this becomes z1 conjugate plus z2 conjugate. And a similar thing happens with multiplication. If I have z1 times z2 and I take the conjugate, this is equal to z1 conjugate times z2 conjugate. And carrying our conjugate arithmetic further, suppose we have something like this, z1 plus z2 conjugate, and we're going to conjugate that. So this becomes z1 conjugate plus z2 conjugate conjugate, which brings us back to z2. So this is just z1 conjugate plus z2. Now, give a quick proof of this. Suppose we have z1 plus z2, and we're going to conjugate the sum. Well, we put it in terms of rectangular coordinates. We have x1 plus I y1 plus x2 plus I y2, and we're going to conjugate the sum. Well, let's regroup what we have within the parentheses. So this is x1 plus x2 plus I y1 plus y2, and we're going to conjugate that. Well, the conjugate of this number is just the minus, so this becomes x1 plus x2 minus I y1 plus y2. Now, we can rearrange this as we regroup. We'll put the x1 and the y1 together. So this is x1 minus I y1 plus x2 minus I y2. Well, since z1 is x1 plus I1, this is z1 conjugate, and this is z2 conjugate. So we have our proof here. z1 plus z2 conjugate is equal to z1 conjugate plus z2 conjugate. Now, for the multiplication, we have z1 times z2 conjugate, and we'll write these now in polar form. So z1 is r1 e to the j theta 1, and z2 is r2 e to the j theta 2, and we're going to conjugate that product. Well, let's put our moduluses together. We have r1, r2 times e to the j theta 1 times e to the j theta 2, and we're taking the conjugate of that. We have the same base as e here, so we can combine the exponents. So we have r1, r2, e to the j, theta 1 plus theta 2, and we're going to conjugate that. Now, when we have it in polar form to conjugate, we just take the minus of the angle. So we have r1, r2, e to the minus j, theta 1 plus theta 2. Now, we separate out the exponents. We have r1, r2, e to the minus j, theta 1 times e to the minus j, theta 2. We associate the subscripts together. So we have r1 e to the minus j theta 1 times r2 e to the minus j theta 2. Well, in polar form, this is z1 conjugate, and this here is z2 conjugate. So we've proven that z1 times z2, we conjugate the product, and it's the conjugates of the individual numbers multiplied together. So these are important relationships, something to keep in mind. We'll be using this when dealing with Laplace transforms. So that sums up complex arithmetic, and in the next video, part 2 of complex numbers, we'll be doing the derivation of trigonometric identities, and there's one in particular that's going to be very important that will carry on over into the Laplace transform video.